What are microwaves? Microwaves are electromagnetic waves that have a frequency of about 2,450 megahertz. Microwaves can penetrate through materials as easily as light through glass. Microwave energy is transformed in materials that absorb microwaves. When microwaves are not absorbed, or when they can't penetrate through a given material, they're reflected. Microwave reflection is the principle behind radar, the first example of a practical application for microwaves. Microwaves were discovered in the early 1940s in England at the University of Birmingham. They were first utilized during the Second World War, during the Battle of Britain. In 1947, an employee of the American radar producer Raytheon noticed that candy laying next to a radar melted. This inspired him to construct a microwave oven. The first patent was granted in 1952, and the first domestic microwave oven appeared on the market in 1961. It was 2 meters high, weighed 350 kilograms, and cost $5,000. Microwaves are most frequently used in telecommunications and data transfer, for heating up and processing food, and for drying various materials such as wood, paper, and ceramics, as well as pharmaceuticals. In the past, microwaves were seldom used in chemistry or the chemicals industry. Only in recent years has their application undergone considerable expansion. But the effects of microwaves on chemical reactions hasn't yet been fully understood. Several research teams in the Czech Republic are studying this subject intensively, especially the team from the Microwave Laboratory of the Institute of Chemical Process Fundamentals.
Jak funguje mikrovlnná trouba?
How do microwave ovens work? Microwaves are generated in a magnetron. They then pass through a waveguide to the oven cavity, where they're scattered and reflected off walls, forming the microwave field. In general, microwaves are consumed by absorption materials, which then heat up. If, however, the materials placed in the microwave field do not absorb microwaves, like glass or china, the microwaves are reflected back into the magnetron, which can then overheat. This can shorten the lifetime of the oven or result in serious damage to the instrument. That's why microwave ovens should not be turned on when empty. Energy efficiency tops out at about 70% when converting electricity to microwaves. Most losses are due to the heat created in the magnetron that has to be cooled intensively. From the chemical point of view, the interaction of microwaves with polar compounds is of special interest. In a normal state, polar molecules are randomly ordered. When placed in an electric field, the positive ends of the molecules orient to the negative pole, and vice versa. But what happens with molecules exposed to microwave fields? The polarity of such fields changes more than 1 billion times per second. This forces molecules to conform to these fast changes, but as soon as they do it, the polarity is again changed. This induces oscillation, vibration, and even rotation, resulting in friction and collision of the molecules, all of which generate heat. Microwave heating differs from conventional heating in terms of the effects which are induced by the microwave field. What are these effects? Microwave heating has some properties that don't exist in the case of conventional heating, such as volumetric heating, superheating, thermal runaway, and hotspots. In the case of volumetric heating, the sample is heated as a whole, irrespective of its thermal conductivity. The maximum temperature is created in the center of the sample and decreases toward the outer walls of the surface. Selective heating takes in objects consisting of two or more materials, in which at least one component absorbs microwaves. For example, in a mixture of water and carbon tetrachloride, the only component heated is water, the upper layer. In the case of a solid object like a pencil, only the graphite is heated. In a compact disc, only the metallic film on the plastic support is burned. Superheating occurs in the case of polar liquids that then boil at a higher temperature than when conventionally heated, for example, 30 degrees higher. For example, ethanol boils at 82 degrees instead of 78 degrees Celsius. Chemists use this effect to accelerate chemical reactions. In the kitchen, this effect can result in the boil-over of Turkish coffee during its preparation. Due to the fact that the microwave field is not fully homogeneous, microwave heating generates so-called hotspots. These hotspots can be detected by UV discharge bulbs placed in the oven space. The formation of hotspots is demonstrated by the non-uniform heating of a silicon carbide bar. Thermal runaway is an exceptional effect, and it takes place only if microwave absorption increases with temperature, for example, on steel wool. Powdered metal materials behave similarly. If a kitchen microwave oven is to be used for laboratory purposes, its microwave field has to be checked regularly for leakage. The Institute of Chemical Process Fundamentals is one of the 6 institutes of the Czech Academy of Sciences that are engaged in chemical and chemical engineering research. I'm very glad to say that the Institute is one of the world's top 5 institutions studying the effects of microwaves in chemical reactions, especially in heterogeneously catalyzed processes. The Microwave Center of the Institute has done recognized work not only in the above-mentioned field, but also in microwave glass melting, and recently in the drying of archival documents. In addition, the Institute has founded a novel branch of chemistry called microwave photochemistry. It's also involved in other projects, like the production of basalt fibers and waste recycling. When catalytic reactions are carried out in the presence of microwaves, the process is called microwave catalysis. The advantage of this procedure includes high reaction rates and yields, as well as high product purity. As a prerequisite, the catalyst to be used must absorb microwaves. A whole new branch of photochemistry has been created by using the ability of microwaves to generate UV irradiation in UV discharge tubes. This has led to the construction of a photochemical reactor with a simple electrode-less lamp that can be directly placed into a flask containing the reaction mixture. The mixture is thus in direct contact with UV irradiation. At the Institute of Macromolecular Chemistry of the Academy of Sciences in the Czech Republic, microwave research has been focused on the use of microwaves in the preparation of cellulose membranes from regenerated cellulose. The outcome of this research is a membrane which is well tolerated by living tissue. When a solution of a compound, like sugar, passes through the membrane containing supported catalysts or enzymes, it's converted into another compound. This is, of course, a required result for processes to be used in biochemistry, medicine, and similar fields. It's generally recognized that microwave heating is a fast and energy-saving form of heating. It heats only the material placed in the microwave field and not the oven space itself. However, the fact that glass does not absorb microwaves and is therefore not heated, let alone melted, turned out to be a serious obstacle. This problem was successfully and simply resolved by concentrating microwave energy onto a minimum amount of space. This launched concentrated local melting that was then transferred to the whole sample. The hot glass then absorbs microwaves, and to achieve the required high temperatures of up to 1500 degrees Celsius is no longer a problem. In addition to the high heating rates and economy of microwave melting technology, its most significant advantage is the favorable effects on glass quality. These results, which have recently begun to be tested abroad, have met with great interest and could substantially affect the world glass industry in the near future. After devastating floods in the summer of 2002 in the Czech Republic, a study of the feasibility of using microwave technology to dry books and archive documents was launched. Unfortunately, using microwaves to dry the documents turned out to be much more complicated due to the disparate components of the materials. Microwave processing could lead to the documents being overheated or even catching fire. Metallic parts and color prints could also be damaged. Fortunately, all of these problems were successfully solved using a novel approach which was tested not only in the laboratory, but on an industrial scale as well. The drying capacity of relatively small dryers amounts to 200 kilograms per day, depending on the amount of water content in the material. The results obtained from the drying of 5,000 books confirmed that this method is not only unmatched by its rate, but also in its safety. At the same time, the high quality of dried materials was preserved. The advantages of this technology has been recently recognized, as documented by the offer of an American firm to buy the license. Microwaves are also the only reliable and fast method for the destruction of molds, fungi, and wood-decaying insects in dwellings. This also includes the famous dry rot, which attacks the wooden parts of houses. Until now, the only recognized solution has been to pull down and completely burn such wooden parts. The use of microwaves offers housing owners not only an original solution, but a real revolution. Microwaves also safely dry all kinds of masonry to a depth of 1.5 meters within a few days. In recent years, the applications of microwave techniques have undergone fast worldwide expansion, and not only in the traditional field, the food industry, but in chemistry and related fields as well. I greatly appreciate the fact that our institute is keeping up with this trend, and that the microwave laboratory of the institute is doing really very well in this respect. On the other hand, I am well aware that we are only at the beginning of our journey. I'm convinced that the microwave chemistry and related fields still have a long way to go.